In recent times, NASA's Voyager 1 and Voyager 2 have passed the heliopause, which is the limit where the Sun's magnetic impact concludes and the surrounding galaxy begins. New assessments of their data are now providing researchers with a clearer understanding of what actually lies beyond this boundary, uncovering surprising structures, particle behavior, and magnetic conditions present in interstellar space. These discoveries are altering how scientists define the actual edge of the solar system and the interaction between our Sun and the Milky Way. In this video, we will delve into what Voyager found at the heliopause, the significance of these results, and the insights they provide about the environment beyond our solar system. Let's begin. Voyager 1 and Voyager 2 were launched in 1977 to investigate the outer planets, yet their most significant contribution occurred decades later, far beyond Neptune's orbit. As the spacecraft journeyed outward, they entered an area where the solar wind, a charged particle emitted by the Sun, slows down upon encountering the nearby interstellar medium. This interaction creates a vast bubble surrounding the solar system known as the heliosphere. The outermost edge of this bubble is referred to as the heliopause. When Voyager 1 passed this boundary in 2012, its instruments detected a sudden decrease in particles from the Sun and a marked increase in high-energy cosmic rays coming from beyond the solar system. These observations confirmed that the spacecraft had entered interstellar space. Voyager 2 later witnessed the same transition from a different vantage point, providing an additional independent set of data. The significance of these crossings lay not just in their occurrence, but in what they revealed about the characteristics of the boundary itself. Scientists had anticipated a broad, turbulent transition area where solar and interstellar particles would gradually combine. Rather, Voyager discovered a comparatively narrow region where conditions shifted quickly and definitively. On one side, the plasma environment was governed by the Sun, while on the other, it was influenced by the magnetic fields and particles from the Milky Way. Close to this boundary, Voyager also identified a zone where solar particles were compressed and heated as they decelerated. This resulted in a layer of high-energy plasma just within the heliopause. The temperatures and particle densities in this area were significantly higher than models suggested, highlighting that the interaction between the solar wind and interstellar space is much more dynamic than previously believed. These discoveries transformed the heliopause into more than just a theoretical boundary. It is now recognized as a physical entity with quantifiable attributes, such as thickness, temperature, and magnetic characteristics. For the first time, scientists could directly observe how a star's influence diminishes and how the surrounding galaxy takes control. The heliopause represents more than merely a line in space. The heliosphere is a protective system that guards the solar system from a considerable portion of high-energy radiation present in the Milky Way. Galactic cosmic rays, originating from distant supernova explosions and similar energetic phenomena, travel through the vastness of interstellar space at nearly light speed. The heliosphere deflects many of these rays, which decreases the amount of radiation that reaches the inner planets. Voyager demonstrated that this protective effect is more pronounced and organized than previously anticipated. As the spacecraft traversed the heliopause, there was a swift increase in galactic cosmic rays, while solar particles virtually vanished. This confirmed that the boundary serves as a filter, distinguishing two distinctly different radiation environments. Previous models had predicted that the Sun's magnetic field and the galaxy's magnetic field would converge at the heliopause at varying angles, producing turbulence and twisted magnetic field lines. However, Voyager discovered that the magnetic field orientation on both sides of the boundary was more alike than anticipated. This indicates that magnetic fields may be linking or reorganizing in ways that remain incompletely understood. Instruments that measure plasma waves also unveiled that the density of the interstellar medium is greater than scientists had estimated prior to Voyager's arrival. This suggests that the Milky Way exerts more pressure on the heliosphere than previously believed, which helps clarify why the Sun's protective bubble is compressed in some directions and elongated in others. Collectively, these findings imply that the heliosphere is not merely a simple spherical shell. Its shape is determined by the interplay between the solar wind and the surrounding galactic environment, resulting in a complex magnetized boundary that evolves over time. Voyager has delivered the first direct evidence necessary to test and refine these models, replacing years of conjecture with empirical data. Grasping the nature of the heliopause has significant practical implications. High-energy cosmic radiation poses one of the primary risks for astronauts venturing beyond Earth's magnetic field. Missions to the Moon, Mars, and eventually further into space will require precise predictions of radiation exposure. Measurements from Voyager help scientists understand how the heliosphere modifies and mitigates this radiation, improving models used for mission planning. There are also ramifications for the long-term evolution of the solar system. The Sun does not maintain a fixed position within the Milky Way. Over millions of years, it navigates through areas of differing density and magnetic activity. If the Sun were to move through a denser interstellar cloud, the heliosphere might contract, enabling more cosmic radiation to reach the inner planets. Data from Voyager gives the first direct insight into how that interaction may occur. These findings have also bolstered the argument for a new interstellar mission. Although Voyager's instruments were designed over 40 years ago, they have demonstrated that the region beyond the heliopause is scientifically rich. A future probe with modern sensors could map the interstellar medium in much greater detail, assessing magnetic fields, particle streams, and chemical makeup over a broad range of distances. For the time being, Voyager is continuing its journey. Engineers are systematically shutting down non-essential systems to conserve power, allowing the spacecraft to transmit data for as long as possible. Every signal relayed back from beyond the heliopause enhances our understanding of a previously unsampled region of space. Voyager has shown that the true boundary of the solar system is a magnetic threshold rather than a far-off planet. Beyond this boundary exists a structured and dynamic interstellar environment influenced by the Milky Way. For the first time, humanity is directly measuring the vast space that lies between the stars.